Okay, I think we should probably get started. Let me just turn the volume up here so we can get the recording. Welcome to Comp 9444, Neural Networks and Deep Learning. My name's Alan Blair. I'm the lecturer in charge for this course. Now, all the materials on for this course will be at this website. We'll be using Web CMS3 for this course. Most of you, I think, are familiar with Web CMS3 from previous courses. That's my email address and my office number. Now, the lectures for this course will be Mondays from 6 to 9 p.m. here in Central Lecture Block 7. Now, it's going to run from weeks 1 to 9 and then 11 to 13. So if you look on the official timetable website, it says 1 to 9 and then 10 to 12. But week 10, Monday of week 10 is a public holiday. Excuse me, it's Labor Day. And so because of the Monday public holiday, we would have to cancel this lecture in any case, so we're going to have a review lecture in week 13 to make up for that. So the pattern will be 1 to 9, and then the mid-session break. Effectively, the mid-session break will be extended because of the holiday. And then we'll have weeks 11 to 13 for this course, maybe not for all the courses. Now, we thought about we won't be having an extended version of this. So we were discussing there might be an extended version of this course, and this other academic called Edwin Bonilla was going to help with the teaching of it, but he's not available because he's got devoted more duties to Data 61, and it's a long story, but we've had to cancel the extension part of the course. So everyone's just been rolled back into Comp 9444. But for those of you who are interested in extension material, we'll try to provide links to online resources and so on that you can then look at. So we try to keep you stimulated in that way. Now, there won't be any organized labs or tutorials for this course. The only contact will be this lecture, but we will have weekly kind of exercises and quizzes for you to go through to make sure that you understand the material, and we'll have some assignments. And what we will have is these labs sessions where we'll have some tutors there or some lab instructors that'll be there to help you with the material. And we tried to pick the times when most of you didn't have any other lectures. So we picked Monday 3 to 4, Wednesday 4 to 5, and Thursday 11 to 12. I hope at least one of those times should be suitable for all of you. And we've booked some labs, and so we'll have some tutors, hopefully 3 or 4 consultants in each lab session, so that there'll be enough to go around. And so those, as I say, they're optional. The attendance won't be taken, but that's a resource for you to use So in the early weeks, it may be to help you get the TensorFlow and stuff installed on your laptop, and then maybe some help with the assignments or with the quizzes or whatever you want to do. So the tutors are all PhD students who've previously taken this course and are quite knowledgeable about the area. So that means, I guess, that you're going to have to sort of be self-directed here. Because there's no organized tutorials, you're going to have to manage your own time and make sure that you keep up with the material. And so it's your responsibility to make sure that you understand the material, go through those quizzes and exercises, and don't get behind. And if you have trouble, go to those sessions and ask for help or post messages on the message boards. Good. Sorry, I was also mentioning, so this course, some of you, so we have a web stream for this course, so I think the enrollment for this course has reached 590 already, and there's not enough space in this theatre. There's only about 420 in this room. However, it's nearly full now, but we know that it's usually, as the course progresses, probably there'll be some space. So if you are enrolled in the web stream, you're still very welcome to come and sit here in the lecture theatre as long as there's a seat available. So there's no real difference between the web stream and the other stream. It's really for fire regulations that we have this system set up. We're not allowed to enroll more people than the seats available into the normal lecture stream because of the fire restrictions. And as I said, if you're in the web stream, if in the unlikely event that every seat is full, you would have to go away. But that's probably unlikely. And some of you, some of you maybe are still trying to enroll in this course, we will try to open up a few extra spaces in the web stream in the next few days so that all of you can enroll. Now, the textbook for this course is called Deep Learning. It's by Ian Goodfellow, Joshua Bengio, and Aaron Corville. I didn't bring my copy in today. I have it at home, but it's a very good book. I think it's in the bookshop. It's good to go and buy a copy, but I think it's still available online for free at one of these websites. So have a look at these websites. I think the content is still there. And the agreement that they had with the publishers, they weren't allowed to provide it in PDF, but actually with most browsers you can pretty easily convert it into PDF, and it looks quite nice. Everything renders properly. Yeah, so go and have a look at this, and we'll be trying to follow the textbook as much as possible. Now, some preliminaries for this course. There are some mathematical things that you really need to understand in order to learn this deep learning stuff. So there's linear algebra, probability theory, and calculus and the chain rule. So some of you may have taken all of you should have done some linear algebra before, perhaps in Math 1A and Math 1B. Definitely should all have done calculus and the chain rule. The probability here, but maybe you need a little bit more linear algebra than what was done before. So just have a look at these sections of the textbook. We will try to revise these a little bit along the way as we go. But if you feel it's probably a good idea within the first few weeks to try to brush up on this material if you're a bit unfamiliar with it. Yes?
Yeah. So for these points, we need to get it done, I guess, by 3 weeks' time.
That would be a good idea if you can.
As such, how well do we need to know this? Do we just need to know it well enough that we can apply it to an assignment or when we have the textbook open? Or should we know it so well such that this is going to be in the exam, like a linear algebra exam?
You should, what you said the first time, you should just need to know it well enough to apply it in the assignment, and it's to help you to understand the concepts. There won't be questions about linear algebra in the exam.
So like quote formulas and stuff. Okay.
No.
Thank you.
Yeah. Where are we? Sorry, I mean, a few of the probability distributions and so on I will go over in the lecture slides, but it'll be whatever's needed will be explicitly on the lecture slides. Okay, these are the planned topics, and I've put the relevant sections of the textbook next to it. Just picking up on the earlier point, the probability, I put sections 3.1 to 3.14. I mean, the probability in the textbook is a little bit, it's sort of phrased in a very sophisticated mathematical notation that maybe is a little bit beyond what's actually needed. But this does cover the relevant sort of topics. So these are the relevant sections of the textbook. So those are the ones you should be concentrating on. So neuroanatomy, perceptrons and backpropagation, hidden unit dynamics, convolutional networks, recurrent networks. So we're image processing. So if I try to divide it into sort of chunks, so there's sort of the neuroanatomy and the perceptrons, the hidden unit dynamics is kind of the maybe the more traditional material, so the brain, parts of the brain that motivate these things, and then sort of the early neural networks and analysis. Then the convolutional networks are to do with image processing. So in terms of applications, we divide it into 3 or 4 major areas. So the first is image processing using convolutional networks, and then we have language processing using recurrent networks, and then we have the deep reinforcement learning, and then the unsupervised learning and generative models. So it sort of divides up roughly into about 4 different application areas, and some of these things are described very well in the textbook. There are a few areas where we have to supplement the textbook with other materials. So the deep reinforcement learning is hardly in the textbook at all, so we provide some additional materials. The generative adversarial networks. I mean, this is the deficit. The textbooks are very well written, but the reason that some things aren't covered well is just because the field is moving so fast. So this textbook was finished. The textbook was written in 2014-15, or 2015, I think. So that's 3 years ago, and quite a bit has happened since then. So we're always making an effort to keep this course up to date. And this really brings the thing home, one thing that really brings the thing home is the fact that, for example, there's a topic called generative adversarial networks, and one of the principal author of the textbook, Ian Goodfellow, is actually a world expert in generative adversarial networks, and yet even that topic is not covered very well in the book, just simply because of when it was written. So we'll have to supplement some of these things with additional materials, but I think there's quite a bit of coverage in the textbook there to at least give you an idea of what we're covering. So the assessment for this course, there'll be some assignments and then there'll be a written exam. The assignments will be 40% and the exams will be 60%, and you've got to get a mark of 50 out of 100 for overall to pass the course, and then you need to get also 40% in each component of the course. So 40%, 16 marks in total for the assignments and 24 marks in total for the exam. Now, we're planning to use TensorFlow for the assignment. We're planning at this stage to have probably 3 assignments. One of them will be about convolutional network. We think the first one will be about convolutional networks. The second one will be about language processing. And the third one will be reinforcement learning. That's what we're planning. Now, I was just in discussions this afternoon with the computer support group about TensorFlow. For reasons that are a bit obscure, the latest version of TensorFlow they can install on the lab machines is 1.3. But some of you, the default version now, if you install it on your own laptop, is 1.9. So we're still sort of sorting out some of those details. We think that there are other ways that we can get access to 1.9 if necessary, but I'll say more next week about what's going on with that. So we'll try to fix which version we're going to be using. And so you may have to write your own code, or often just take some existing code and run it and analyze the results and maybe make a few changes to it. So you don't have to be an expert programmer, or you don't have to be an expert TensorFlow or Python programmer to complete this, but you will have to know something about Python and TensorFlow. So if you're not very familiar with Python, you'll probably have to brush up on this. So we'll put some links on the course website for a couple of tutorials about this. And again, the tutors will be available in the lab sessions from next week to help you. Plagiarism is taken very seriously in this school. At this stage, I think most of you are aware of this. So don't give your code to anyone else. If they ask you for your code, just say no. Don't put your code in a place that's publicly accessible. If you have it on your CSE machine, set the permissions so that it's not readable by other people. If you put it up on GitHub or GitLab, again, select the option so that it's not publicly readable, and so on. Okay. Now, there's some related courses in this school in the field of artificial intelligence. So there's the artificial intelligence course, which ran last session and will run again next session. There's 9417, machine learning and data mining, I think will run in first session next year. I think 9418 is running now. I think that's the course Edwin is teaching, Advanced Topics in Statistical Machine Learning. 4418 is more to do with symbolic methods. That's running in this session. Robotic software. Is anyone enrolled? Let's have a show of hands. Who's enrolled in 9418? No one. Oh, a couple of people. Is anyone enrolled in Comp 4418? Yes? Okay. What about robotic software architecture? It may have a different course code for the postgrads. Okay, you're enrolled in that. Machine vision, I think, is running this session as well. And then if you're an undergrad, you can think about doing a fourth-year thesis topic in an AI-related area. Okay, so that's kind of the administrative side of things. Are there any questions about this? Okay, so we start by talking a little about the brain and neuroanatomy. Now, this is going to be a fairly, we're not going to go into great detail about this, and this is more kind of background knowledge rather than sort of examinable material, but a neural network, what is a neural network? Well, it's a massively parallel distributed processor made of simple processing units. Knowledge is acquired from an environment through a learning process, and the knowledge is stored in synaptic weights. So why do we want to study neural networks? Well, partly because they're biologically inspired. They have good learning properties. They're well adapted to certain types of tasks, and they're continuous and nonlinear, so they sort of strike this balance where there's a certain amount of nonlinearity. If you have a system that's completely linear, if you compose things that are linear, it always stays linear, and you have limited functionality in a linear system. So to do some interesting things, you need nonlinearities. But in neural networks, we have controlled nonlinearities. So you have multiple layers, and at each layer, you have a certain amount of nonlinearity, but kind of just enough, not too much nonlinearity, just enough to kind of get the job done. And fault-tolerant and graceful degradation, this is kind of maybe this is historical motivations or to do with hardware, but if you start with a neural network, and let's say you have a neural network that's built in hardware, and then some of the connections break, well, the thing will still perform the task that it was trained for reasonably well, but as you break more and more connections, the performance will kind of decrease gracefully, and this is in contrast to like a kind of traditional symbolic computer program where if one character is wrong or one instruction is wrong, then the whole thing can collapse. Some of you may have seen this picture before. This is just an example of parallel processing in the brain. So there's an animal in this picture somewhere. Is anyone who hasn't seen this picture before? Okay, among those people, do you think can you see an animal there? And what kind of animal is it? A dog. That's right. Yeah. So this is its, that's its face there, it's sniffing the ground. These are its front legs, these are its back legs. Yeah, so it's, and then if there's a sort of, some people from certain African countries actually see a hyena instead of a dog. And the hyena is facing the other direction. So this is its ears, that's its eyes, and that's its mouth. So you've got this sort of head of a hyena here, and then the same legs as the dog. So what people see can, to some extent, be culturally vary according to their cultural background. So just a little bit of history about artificial intelligence and also neural networks. So AI kind of goes back to the ancient Greeks. So there was this traditional this traditional kind of distinction between rationalism and empiricism, whether thinking is something that's innate, that's born into us, or whether it's learned from experience. So this old argument about nature versus nurture. And Kant, in his critique of pure reason, tried to kind of argue for some sort of compromise between the two. Descartes wrote about this mind-body dualism. So this is the idea, what is the mind? Is the mind actually part of the brain? Is it a physical thing? Is it an epiphenomenon of the brain? Can the brain, maybe the brain can influence the mind but not the other way around, or maybe the brain is something sort of extra material. Maybe the brain is something sort of maybe the mind is something supernatural somehow, which can influence the brain, the body. It can go both ways. And these arguments still are going on today. It hasn't really been resolved, the answer to that question. But of course now it becomes additional questions. If we do build a machine that exhibits intelligence on the level of a human, would we say that machine has a mind? Would we say that it has a brain? Obviously it has a brain, but does it have a mind? Does it have a soul? Would we give it legal rights? And so on. Just mentioning a couple of other things. So the field of psychology was basically started by Sigmund Freud. In 1899 he wrote his famous book on the interpretation of dreams. So his big contribution was to point out the importance of the subconscious mind. He made us realize that there's actually a lot going on in the brain beyond what we're consciously aware of. It's only a tiny fraction of it that we really are aware of, and there's a lot of other computation going on underneath. And then we have Skinner behaviorism, so the idea of learned behaviors as a kind of stimulus and response, and is that adequate? Well, so he did these experiments with pigeons, and other people like Pavlov did the same sort of thing with dogs, where you train a pigeon to to perform some task in order to get reward. So again, these arguments are still going on today. Is this sort of stimulus response idea sophisticated enough to explain human behavior, or do we need something more complicated? Now, so that's sort of theories about the mind. Now, if we look at artificial intelligence, it sort of began in a way in the 1600s with Pascal and Leibniz. So they had this idea of the mind as a kind of mechanical adding machine or calculator, and they had this very kind of idealistic idea that every dispute, I forget which one of these guys had the idea that any dispute could be resolved through logic. If two people were disagreeing about something, that they should just sort of sit down together and say, calculimus, let us calculate this. And they would do some calculations, and then one of them would understand, oh, okay, I was wrong and you were right. So he had this kind of naive idea. But of course, it's not that simple, because we've got all of this fake news, and it's often very hard to say what's really true and what isn't. But that's again, these things are old, but they're very current. These are still pressing issues in the modern era. Where are we? Wolfgang von Kempelen. So most of you are familiar with this phrase, Mechanical Turk, now because of the website. Yeah, Wolfgang von Kempelen made this kind of magic trick. He made this machine that looked like it was playing chess, but actually it was just kind of a mannequin, and there was a human sitting inside operating it. So it was a trick, but it was a very popular trick, and it inspired other people, including Charles Babbage and Ada Lovelace. So Babbage saw the Mechanical Turk chess player on display in a royal exhibition in London when he was 8 years old, and when he grew up, he really kind of was obsessed with this idea of whether you really could get a machine to do things like playing chess. He designed a machine that would play a simpler game of like noughts and crosses or tic-tac-toe, and he designed a couple of other machines, that one of which was sort of a general purpose computer, but he never really had the money to build these machines. But it was proven in the early 1990s that it would have been possible to build those machines according to his designs with the technology of the day if he had had enough money. And he was the hardware guy, and Ada Lovelace, the daughter of Lord Byron, was the software person. She's sort of recognized by most people as the first computer programmer, and there's a programming language named after her called Ada. And then we get to logic. So the first order logic, predicate logic, Boole and Frege. And then we get to the Turing test. So Alan Turing talked about this idea of trying to test whether a machine is intelligent or not by having it interact with a human and have the human try to guess whether they're interacting with the machine or the human. So that was discussed in 1950. And then the first AI conference was held in 1956 in Dartmouth. So that's sort of AI in general. Now, if we concentrate specifically on neural networks, well, in 1943, McCulloch and Pitts published a mathematical model of a single neuron in the brain. So we'll get onto that a little bit later this hour. And in the 1940s, there was a guy called Norbert Wiener at MIT he invented the term cybernetics. It's kind of another word for robotics. We don't hear the term cybernetics as much these days, but it comes from the Greek word kumernatos, which means the person who's steering a ship. So it's kind of got this nice idea about control theory. Now, Alan Turing is famous for his code breaking and also for the Turing test and the Turing machine. He was an extremely influential person. But interestingly, right near the end of his life, he wrote about what we would recognize today as neural networks or primitive neural networks. In 1950, his paper about the Turing test was published, and at the same time he wrote this treatise. It's very kind of forward-thinking for its day. He talks about the importance of embodiment. Some of these two essays weren't really published until later on after his death, but he talks about the importance of embodiment. If you're a robot with a physical body, you can learn things that you wouldn't be able to learn if you didn't have a body. He talks about the importance of learning. You can't just program everything in. You need some sort of what we would call reinforcement learning today. And he also describes these sort of networks that are a bit like electrical circuits, but there's some sort of neural network. Okay, so for the 40s. And then you kind of go on. So Oliver Selfridge did early work in pattern recognition. So this is, I guess, mainly image processing and perhaps sound as well. 62, Hubel and Wiesel were describing neural connectivity in the visual cortex. So again, we'll talk about that in a little bit more detail. And the Rosenblatt perceptron we'll talk about as well. So this is sort of the early history of the neural networks. And Yeah, I apologize for all this historical background, but I think it is interesting to see all of this in context. So you had neural net. So for a long time, you had these two kind of rival approaches. You had the neural network approach or the connectionist approach, and then you had like there were other people who said that the best way to achieve AI is through serial symbolic processing. So at that 56 conference that I mentioned, Alan Newell and Herb Simon displayed this thing they called the logical theorist. So this is that conference. Most of the people who came to that conference just sort of waffled on about some ideas, but these guys actually had a program that they'd implemented, that they demonstrated, and I think it was it did some sort of logical deduction. John McCarthy, so John McCarthy invented this language called Lisp. So for a long time, Lisp was used as the main artificial intelligence language. The late 50s, 59, also Arthur Samuel was working on, he wrote this very impressive checkers program for its day. So that was the early work in game learning and also included some reinforcement learning. But I guess Lisp, it's interesting to see how old Lisp is. So there was another language called Fortran, which was used for engineering purposes. And this Lisp actually sort of processed things by having lists of items. And it dates back to about the same time. Both of those languages were devised in around about 1959, and so these were the first high-level programming languages. Before that, everything had to be done in machine code or assembler, and now you could write a high-level language. But the symbolic processing dates back the same era as numerical processing. And then, where are we? 65, Joseph Weizenbaum wrote this program called ELIZA. So this is one of the early attempts to write an AI program. So this was a program which would carry on a conversation with you, and it pretended to be a psychiatrist. So it was sort of, it was written in Lisp. It was very short, actually. It was only a few pages of Lisp, but somehow it managed to fool people into thinking that it was intelligent. But it would just, you would say, it would ask you, how are you today? And you'd say, I'm feeling tired. And it would say, why do you think you're feeling tired? So it would sort of try to repeat whatever you said. It would try to repeat it back to you. But it was smart enough to sort of change I to you, I'm to your, and so on, like to sort of change around these pronouns. And then if you mentioned that you had a fight with your mother, it might, a little bit later, it might say, tell me more about your family. So a lot of it was just sort of pattern matching. And if it didn't understand what you said at all, it would just say, please go on. So that was kind of enough to fool some people. But it was kind of a joke. The thing is, Weizenbaum wrote it as a joke. He said, well, AI is really a long, long way off because with current technology, all we can do is this. But other people took it in a different way. Other people thought, oh, this is really fantastic. All we've got to do is take this and make it a little bit better. And so this led to what we call expert systems. And one of the most famous expert systems was called Dendril, that was tried to do medical diagnosis. So you'd say what your symptoms are, and it would try to guess what was wrong with you and what medicine should be prescribed or whatever. And it was all written with these sort of logical rules and so on. Now, I mentioned that there were these two rival paradigms, the neural network approach and the symbolic approach. Now, in 1969, Marvin Minsky and Seymour Papert they published a book called Perceptrons in which they highlighted the deficiencies of neural networks as they currently existed. And in addition to writing the book, they also went down to Washington and kind of lobbied the government funding agencies to try to, went down and told these guys, tried to persuade them to cut off the funding to neural networks and divert it to symbolic systems, which happened to some extent, although in a way it backfired because the funding, so this was in the United States, but a parallel thing was going on in Britain with the Lighthill report and so on. In a way it backfired because the funding agencies just thought, well, look, these guys are arguing amongst themselves. They're probably all idiots, so let's just cut off funding to all of them. So between 1969 and 1985, there was this period that's sometimes known as the AI winter, or whether you date it from 69 or 73, but anyway, up to 1985. So during that period, it was very hard to get funding to do any kind of AI research. The little work that was being done was mainly about expert systems. There was hardly any work done in neural networks or machine learning. Those things were very out of fashion. There were a few exceptions. There were a few researchers like Grossberg and Cahonen and Paul Wehrboss who continued to work on these things, but it was very few. Yeah. But then somehow after 1985, interest in this area got revived. Okay, and then this is sort of the reason why the expert systems failed is yeah, okay, so I'll say a little bit about this. Yeah, again, this is sort of the history, but so the idea then was it seems funny to look back on this from a modern perspective because we all accept machine learning as such a important thing these days. But at that time, the idea was that you would get an expert and you would interrogate if you wanted to write a program to do medical diagnosis, you would get a doctor and spend a lot of time interviewing that doctor and why did you make this decision? In this situation, what decision would you make and why do you make that decision? And then you try to sort of, whatever they say, you try to turn it into rules. And the idea was if you could just interrogate enough experts long enough and code in enough rules, then the system would be able to repeat what the expert would do. But it led to two problems. So the first one is the combinatorial explosion in search space. So you have facts and then you have rules, and from the rules you can deduce new facts. But the number of different facts you could potentially generate, you could generate millions of facts, but most of them are irrelevant, so there's a difficulty in generating the relevant facts. And also it's difficult to formalize everyday knowledge in a computing system. So there's all sorts of examples of this, like here's just one example. If I'm if I have a cup that's red and if I turn it upside down, it's still red. But if I have a cup that's full of water and I turn it upside down, it won't be full of water anymore. It sounds stupid to say that, but the expert system wouldn't know that unless you actually type it in as an explicit rule, right? And it just, there's no end to it. If you just you have to keep typing more and more of these rules in. Okay, so where are we? 1985, right. So there was the AI winter, but then from 1985 onwards, we had this sort of neural network renaissance. So 1986, they had this summer program in San Diego on connectionism and neural networks, and several important papers came out of that, including this paper about backpropagation by Rumelhart, Hinton, and Williams. In the late 80s, you had some important applications of neural networks, so including early work in autonomous driving. So Dean Pomerleau's group in Pittsburgh had some autonomous driving going as early as 1989. Alvin stood for the autonomous learning vehicle in a neural network. And then in the 1980s, you had a sort of more, 1990s, you had more principled approaches. For a while, neural networks themselves sort of fell out of popularity a little bit, and there was more interest in things like support vector machines and Bayesian models. But then when you get into the 2010s, neural networks came back into popularity largely because of the success on tasks like image classification and more recently language processing and Go and so on. And there's new areas that may become fashionable in the future. So spiking networks might be something that becomes good when new hardware is developed to support it. And evolutionary methods compared to gradient descent methods are also, that's a big kind of discussion that's now going on. Okay, so this is a very exciting time for deep learning. Okay, so here are some important applications of deep learning. So I mentioned image processing, so classification of images. You know, you're given an image and you have to say whether it's a picture of a bird or a cat or a pumpkin or whatever. And also segmentation. You're given an image that has multiple objects in it, and you have to identify which object is where. Then we have language processing, so translating from one language to another, trying to figure out the meaning of a word if it's has multiple meanings, sentiment analysis. You're given a little blurb about a movie or a tweet about a movie or a stock, and you have to quickly say whether it's a good movie or a bad movie based on what's written there. Or if it's written about a stock, whether you think you should buy or sell the stock based on what's said. So this is, you know, very primitive, I guess, sentiment analysis where you just get a positive or a negative, but then you can do other related tasks like topic identification and so on. Is this a tweet? Is this a tweet about politics? Is it about something else? Is it potentially about a terrorist attack? Then there's applications that combine images and language. So you're given an image and you have to automatically generate a caption for that image. Or you're given some text and you have to find an image or a movie or a little video clip that text is relevant to that text. And game playing, so AlphaGo and deep Q learning for Atari games and other things. And I could have added image generation at the bottom of this list. Now, if you're interested to read more about the history of neural networks, these are two very interesting review papers. So the top paper was written by these Canadian groups in Toronto and Montreal, and kind of focuses mainly on recent work. It hardly mentions anything before 2012. It's all just the recent stuff. But then several people who've been working in this area for a long time got angry about that review because, you know, they felt it was unfair that they didn't mention anything earlier. They pretended that they'd invented things that actually existed before. The person who got the most angry was this guy called Jürgen Schmidhuber, who's quite an interesting kind of character based in Switzerland. So he wrote his own review article, which is kind of the opposite. It goes all the way back to the 1960s and traces through a lot of these, the history of this stuff from the early days. So it's quite interesting to go and have a look at both of these. Okay, any questions about this history stuff before we move on to neuroanatomy? Where are we? 7 o'clock. Okay. Good. All right. So let's put all that aside for the moment, and now let's concentrate on the brain. So this is where all of this is sort of motivated from, is studying the human brain. And we talk about the central nervous system, which consists of the brain and then the spinal cord. And then there's the peripheral nervous system, which is all the kind of nerves and so on throughout your body. Now, if we just look at the brain has several regions which have these fancy Latin names like the thalamus and the hypothalamus and so on. And then, well, at the back of your brain is this thing that's called the cerebellum. The cerebellum literally just means the little brain. I think it's a kind of looks like a smaller version of the brain sitting at the back there. And I guess, you know, I didn't bring my Kandel, Schwartz, and Jessel, but there are these, you know, textbooks about the brain that are very thick, and there's a huge amount of information. People spend their whole lives studying just one little part of the brain. So all we can do is really just give a very kind of quick overview. But I guess the main thing is that these parts in purple here, the spinal cord and the cerebellum and the brain stem, they're sometimes referred to as the reptilian brain because they're very, very ancient. So these structures here have hardly changed over periods of millions of years. If you look at lizards and crocodiles, they have essentially the same structures here as what we've got. So these things, they cover very, very low-level behaviors. So they regulate your breathing, your heartbeat, your body temperature, that kind of thing. And then when there are situations, when people are in situations of extreme stress, like they're in a bank and someone comes in with a gun and holds up the bank, sometimes the rest of the brain sort of shuts down and this ancient reptilian brain takes over, and people just act by instinct. And sometimes sensory information gets filtered out in that process. It's interesting when people are interviewed afterwards, sometimes they remember what was said very, very clearly, but they can't remember what they saw. Or the other way around. They can remember what they saw very clearly, but they can't remember hearing anything. And it's actually because certain sensory pathways get blocked in those extreme situations. Okay, so that's the very ancient part of the brain. Now, the most modern, in contrast, the most modern part of the brain is this part here called the cortex. So the cortex comes from a Latin word meaning the bark of a tree, because that's kind of what it looks like. And if you look at the brain of a human compared to the brain of another animal and ask, well, what's really different about our brains, then basically the answer to that is the cortex. So our nearest relative is like the chimpanzee, and the chimpanzee brain, famously the DNA of a chimpanzee is 98% the same as a human. If you look at the brain, it's somewhat similar as well, but it wouldn't have, the chimpanzee wouldn't have this cortex, or it wouldn't be as big, nearly as big as what it is in the human. So it's this whole kind of outer layer of the brain. So our brains are bigger than that of other animals because of the cortex. And because we have it and other animals don't, that's the main reason we suspect that this is where higher cognitive functions go on. And it's also maintaining this big brain and cooling it and keeping it, supplied with blood and oxygenated requires quite a bit of energy, which is why we have to eat more food than other animals to keep our brain going. The cortex is divided into 4 lobes: the frontal lobe, parietal lobe, occipital lobe, and temporal lobe. Sorry. And it has these higher level functions such as voluntary movement and language and reasoning and so on. So I don't want to, I guess I don't want to go into too many details about this, but there are a lot of interesting things about this. So well, let me just say something about language. It's interesting. I mentioned about chimpanzees. If you can try to, functions aren't really localized in the brain too much, but there are some areas that are strongly connected with language or whatever. The main reason we know this is from looking at people who've had injuries in a certain part of the brain and then experimenting on them to see what cognitive deficits they have. And if you look at the areas that are associated with language in a human and then you look for the corresponding part of the brain in a chimpanzee, it's actually, that part of the brain actually controls the hands, not vocalization. So this has led some people to suspect that sign language may have occurred before speech. Okay, so a lot of this I've already mentioned. So the brain stem, it regulates all these low-level bodily functions. And the cerebellum. And then the limbic system. Yeah, okay. Well, let me get back to this, back to the cortex. So one of the interesting things about the cortex, it controls sensory and motor functions. And you can actually sort of make a mapping that a certain part of the brain will control a certain part of the body. and also the sensory information from certain parts of the body will go to certain parts of the brain, so you can sort of make a map of the body inside the brain. And if you look at the sensory functions, it's kind of laid out like this. So you've got the face, hand, arm, and leg, and there's more brain area devoted to some parts of the body than others. So your fingertips are much more sensitive than your elbow, right? So there's actually more brain area devoted to your fingers than there is to your elbow or your knee. And the sensory information generally comes in here. And then there's also the motor function. So which part of the brain controls the fingers? Which part controls the legs? You can map that out as well, and there's sort of cross connections here. So these are two different lobes of the cortex, but there are connections going across between here and here, and these things tend to line up. So the part of this cortex which controls the fingers tends to be lined up with the sensory part of the fingers, which sort of makes sense when you think about it. So that's the sort of sensory and motor functions. And then, as I said, you can roughly say where certain other functionalities reside. And generally speaking, smell will be here. It makes sense for remember, this is the back of the brain, this is the front, so this is the bit that's just above your nose, so it sort of makes sense for smell to be processed there. Hearing tends to be here. Now, speech and language, vision. Okay, so vision, the primary visual cortex is actually at the back of your head. So the light goes through your eyes and goes into the back of your head. So that's where the vision image processing starts, is the primary visual cortex, and then it moves on to the secondary cortex and so on. But this is why if you get hit on the back of the head, your vision becomes blurry for some period of a few seconds and so on, because it's disrupted the primary visual cortex. And as I say, speech and hearing tend to be in these areas. And then for left-handers, it's a little bit different. So for a right-handed person, these mappings tend to be pretty regular, that speech is always in this area and so on. For a left-handed person, there's a little bit of variety there. A left-handed brain isn't as simple as just the mirror image of a right-handed brain. Okay, any questions about this? Where are we? 7:13. Okay, I think we'll take a 10-minute break at this stage, and then we'll come back and talk in detail about at the scale of an individual neuron. How's it going?
I'm good, sir.
No.
Sir, I'm curious about a question regarding the mathematics question.
Oh, yes.
I have taken course already, like lesson on linear algebra,
Oh, yeah.
the probability, the foundations, and but I know about the basics of like let's say the determinant or taking the transpose or matrix, but I don't have much good idea about why we are taking the transpose here or why we are taking the here or the latest stuff operation of the matrix. So I mean, how do you suggest like was like we have a system like over like we have been given the equations like take transpose of this equation, but no one knows why we are doing this or what problem it is to be involved in application. So I mean, what revising on the question of these concepts about the math, how do you feel like
I mean, it's transfers, yeah, I guess it's mainly when we get, probably mainly in the language classes. I mean, you have a matrix, so when you have a vector, you can write it either as a column vector or a row vector. So, if you have a matrix and then a row vector on the right, then when you multiply it, you'll get another row vector. But if you've got, if you've got a column vector, you multiply with the matrix on the left and then a column vector, and you'll get another column vector. But if it's a row vector, you have to multiply with the matrix on the right and the vector on the left. So a lot of it's about that. Like, then if you, let's say you have a matrix M and a column vector X, you have M times X. But then if you want to have the X on the left, you turn the row vector, the column vector into a row vector, but then you have to take the transpose of it. So a lot of it is just simple things like that.
So, how do I switch on the Google keywords should I use? So, when I switch previously in Google, then they mostly say like how to take a transpose or how to take like inverse of a matrix. But
It doesn't say when.
when, why, this kind of stuff.
A lot of it is mainly what I said, you know, if you want the thing to be a row vector instead of a column vector, you often take the transpose and multiply it on the right.
These are just examples, not specifically, I mean, these portions are bothering me, but these are just examples.
Yeah.
I mean, of course, there are other stuff about the real algebra. So, I mean, so the other stuff, and just, I was just quoting examples like this. So, overall, what keywords should I search or what books can I search on the internet? How can I maybe...
Good question. I mean, we've been talking about this. What we really need is to have we should have some short course that's just mathematics. The mathematics that's needed for deep learning. That's what we really need. But where to really find this information? I'm not sure, but I'll have to think about it. Yeah, if I find some relevant stuff, I'll let you know.
And today we will just discuss the background and
Mostly the background, maybe the perceptuals.
so I mean mostly about the history and the philosophy.
Yeah. Moving into industry pretty quickly. I mean, it's obviously, for example, language processing. A lot of systems use language processing. Some of them were previously done with different methods, but are now being updated. Yeah. I get the feeling a lot of companies are looking for this kind of people. They're having trouble at the moment finding people. So this will be a good position. People who can take this stuff to the lawyer and no, this is just background.
So a lot of the software start
That's right.
That's funny. I was enrolled in like April.
Oh, yeah.
I don't think we're moving on to
Oh, yeah, I spoke to Phoebe today. I think she's still in the process of
as long as you guys.
Okay, we might resume. So the body, the human body is made up of cells, billions of cells, and there's of course different kinds of cells, but the cells in the nervous system are called neurons, and they are specialized to carry messages around through electrical signals. So a cell, they are, as I said, they are cells, so they have all the usual stuff that a cell would have, right? So they have a nucleus, and inside the nucleus is the DNA, and then there's mitochondria, and there's, the mitochondria play a role in giving energy to the cell, so food gets digested and it gets turned into energy. So because it's a cell, it has to do all the things that a cell normally does to keep itself healthy and so on. But cells are normal. Most cells would just be sort of roundish in shape. But in the case of a neuron, the surface of the cell gets spread out into this very, very strange shape. And so you get these long bits that are stretching out that are called dendrites. So dendrite comes from the Latin word for a tree. All of this is based on Latin words. And there's the nucleus, so then that's the dendrites, and then there's an axon. So there may be multiple dendrites, and then there's this axon. And what happens is that the way the electrical signals actually are transferred is that electrical signals can come in from electrical signals from other neurons can come into these dendrites, and like charged particles called ions come into the cell, and that raises the voltage inside the cell. And when the voltage reaches some threshold, then we say that the cell fires and an electrical signal will go along the axon. So it's a very kind of non-linear process. It's not just that the ions come in and sort of randomly wander through here. They come in pulses. The voltage builds up to a certain threshold, and then an electrical signal will pass along the axon, and then there'll be a period of time before the voltage builds up again, and then another signal will go through. So it's sort of these pulsed signals. And the axon can vary in length from just like a millimeter to a centimeter. Now in the motor system, what's actually drawn here is a special kind of cell in the motor system that has a very long axon. The axon could be actually half a meter in some cases. And if the axon is very long, then it has this myelinated sheath around it which serves the purpose of keeping the charge, preventing the charge from dissipating and allowing the electrical signal to pass along the whole length of the axon. And if people get certain kinds of motor neuron disease, the axon becomes demyelinated, and then people have these very sort of jerky movements. So these motor neurons are very special because the reason the axon is very long is so that you can react very quickly. So if you put your hand on a hot stove, you pull your hand away very, very quickly, probably before you're even consciously aware of it. The signal doesn't even get all the way to your cortex. It only gets up the spinal cord to the brain stem. And then a signal goes back telling you to move your hand. And so that particular signal may only go through a very small number of neurons. It might only go through about 4 or 5 neurons in order to get all the way from here to here, because of these special kind of neurons with long axons. But inside the brain, there's quite a variety of different types of shapes. So this one here in the top left is one of those motor neurons. So you see how this has got this very long axon. Well, these are just a couple of other examples. So this here is this is from the olfactory bulb. So this is to do with the sense of smell. So, excuse me, yeah, you can see the dendrites at the top there. So those dendrites are receiving signals from other cells, and then this is the axon. And these ones are interesting here, these Purkinje cells. These occur in the cerebellum, that very ancient part of the brain. They can have up to 10,000 dendrites. So you can have one neuron that's receiving signals from 10,000 other neurons. And interestingly, if you turn it on, these things are very bushy in 2 dimensions, but they're very flat in the 3rd dimension. So when you turn this thing sideways, it actually looks like that. And this one here is this is a pyramidal cell. That's what's typically found in the cortex. So we talked about the cortex. That's unique to humans. And what you typically find here is that the cortex has layers, and that most of the connections are within a layer. So this is the cell body here, and you don't see it too well in this picture, but the majority of connections spread sideways within one layer. So there's a lot of connectivity within a layer, but then there are a small number of connections that go out into other layers. And then this is the axon, and then so the information is mainly traveling in a particular direction, but can go a little bit, some signals can go backwards as well. So it determines this pattern of connectivity. And these are just a few of many, many other examples. Now, okay, so then you get a connection between, so these things are, the axon, every neuron has only one axon, but the axon can actually spread out to be its own kind of tree, as you see here, and then these things here, these axon terminals, can touch the dendrites of the next neuron. So that's how you get these signals connecting to each other. And they can be excitatory or inhibitory. So if it's excitatory, it means that if this neuron fires, it makes it more likely, it increases the voltage of the next neuron and makes it more likely to fire. Some of these, the majority are probably excitatory, but some of these connections are inhibitory. That means that if this neuron fires, a different chemical reaction happens which actually makes it less likely for the next neuron to fire. So you can have excitatory and inhibitory connections, and if you look closely at the chemistry at these junctions, again, there's a huge amount of complexity here that we usually try to abstract away, but there are some people who devote their whole lives to studying these kind of things. There's different kinds of channels. There's calcium channels, there's sodium channels. But basically, this is sort of a cartoon version of what goes on. So this is the synapse from one neuron. So electrical signal is built up here. And then you have certain channels here which are actually sort of little gates, if you want, inside the cell wall that are capable of opening up and allowing ions to pass through them. And you have these synaptic vesicles, which are little kind of balls of charged particles that are floating around there. And then when the voltage reaches a certain threshold, it causes these vesicles to kind of break open, and the charged particles get released, and the gate also opens so that they can flow through this gap to the dendrite of the next neuron. And then you have these receptors that open up to allow the charged particles to go through. So this actually, for our purposes, we try to simplify this and just write a very simple equation to but underneath there's all this kind of complicated chemistry going on. And soon we'll be talking about backpropagation and how learning occurs in neural networks. Well, we still don't fully know how learning really occurs in the brain. I mean, we're very, very ignorant about this, but there is a certain type of learning we kind of understand, which is called Hebbian learning, that somehow if one neuron fires and it causes the next neuron to fire, that connection somehow gets strengthened. That there's little chemical reactions that, these things built up and then this fired. Right, so this fires and then that builds up the charge in this neuron. And then somehow if that very soon afterwards causes this neuron to fire, there is some chemical signal that actually goes back and says, that the next neuron fired very soon after you released your chemicals. So the assumption is that, because you were one of the last guys to release chemicals before the next neuron fired, you probably provided some important information, and something goes on that actually makes this connection more likely to, makes ions more likely to come out of this connection later on. So there's this kind of Hebbian learning where, if a neuron fires, if this neuron fires just before the next neuron, this connection somehow gets strengthened. So we know we sort of understand how that happens at a micro level, but how that actually causes the brain at a macroscopic level to learn something useful is still a bit of a mystery. But we just kind of, do something analogous sort of in artificial neural networks. It's not the same in details. And this is just a close-up of these ion channels. So this is these receptors here. Yeah. So somehow, when enough neurotransmitter, so the neurotransmitter, the ions are there, and there's also these other chemicals are released that are called a neurotransmitter. And when enough neurotransmitters lodge onto there, it causes this thing to open, and then the charged particles pass through. Okay, so that's like the microscopic level with just one neuron, but what about the big picture? Well, the brain has 100 billion neurons, and on average, 10,000, yes, that's right, 10,000 synapses each. So on average, one neuron is connected to 10,000 other neurons. And the latency, what do we mean by latency? Well, then if one neuron is connected to another, what is the time gap between the time when this neuron fires and the time when that neuron fires? It depends on the type of neuron, the type of channel, the length of the axon, but typically perhaps 3 to 6 milliseconds. So there's a sort of paradox here in a way that when you think about a modern computer, things are happening on the order of gigaflops, right? You're going to have a billion. If you write a program in C and compile it into assembly language, those assembly language instructions are being executed on the order of billionths of a second. But in the brain, one neuron firing and then the next neuron firing, this is only happening on the order of millionths of a second. So this is, in some sense, the things are happening much slower in the brain than in a digital computer, and yet it's fast enough for us to do impressive things in real time. When you listen to someone speaking, you can understand what they're saying in real time, and it only takes you perhaps 100 or 200 milliseconds after a word is said before you know what word it was. So we managed to do things that computers still can't do, even with this very slow hardware. But part of the reason is because it's massively parallel, right? So traditional CPUs only executed one instruction at a time. Now we have modern GPUs that can make use of parallelism in certain situations. But what's happening in the brain, it's making use of parallelism. So there might, each operation is taking a few milliseconds, but there's maybe 10,000 operations that are happening at the same time. So it's making use of this parallelism. Okay, now when we talk about the big picture, as I said, there's a lot about the brain we really don't understand. I mean, what's really going on in the cortex and so on, even today, realistically, we know very little about it. But there are certain parts of the brain that we understand very well. And the bits that we understand very well tend to be to do with perception and action. So the motor system we understand very well. What I was saying before, what happens when you put your hand on a stove and pull it away, we understand exactly what's going on there, how the signal gets up to the brainstem and how it goes back. And this is from people doing experiments with frogs and electrical probes and that sort of thing. So the motor system we understand well, and the perception system we understand well. So we understand very well the vision system, and we understand the hearing system and the smell system. So it's kind of like there's inputs, there's parts of the brain that process the inputs, and there's parts of the brain that make your body move, and we understand both those ends quite well. But then what goes on in the middle is still a bit of a mystery. Okay, so let's talk about the vision system. And this is what goes back to this Hubel and Wiesel that I mentioned. So these guys, so these guys did experiments mainly on cats, I guess. They would, it's a bit sort of gross, to think about this, but they would get a cat and you know, put it in an apparatus where it can't move its head too much, and they'd present things for it to look at, and they'd have a little probe that would measure the response of certain neurons in the visual cortex. And what they found is that certain neurons only respond to line. You know, if you see a line in a particular angle, you know, there might be a neuron that only responds when you see a line at that particular angle. You know, and there's another neuron that only responds if you see a line at that angle, and another one at this angle. And these neurons are arranged in a kind of geometric pattern. So the ones that respond to this angle, let's say these neurons respond when there's a line at this angle, and then the ones next to it respond when the angle's a little bit different and a little bit different. So it could be, in a way, hardwired. You know, there's big debate about nature and nurture. It's sort of hardwired in a way that the thing's going to develop like this, but you need visual stimulation in order for it to develop properly. So if you, there are some people who are born blind. If you're born blind, the part of the brain that normally processes vision won't develop properly because it's not being presented with any stimulus, and sometimes that part of the brain will get taken over by other things. So perhaps the auditory system. So people who are blind from birth often have a more acute sense of hearing than other people because a bigger part of their brain is devoted to hearing. And yeah, if you have famous cases where people have been blind since birth, and then at the age of 20 or something, some medical procedure is able to restore their sight, but they won't. In the beginning, when their sight is first, you know, when their eyes are first sort of fixed, they really can't actually make any sense of the world around them. It takes them some months for this kind of thing to develop. And more has been done on this since. So there are actually some. So this is in V1. Right. So the primary visual cortex, as I said, is at the back of your head, and then the signals move on to the secondary visual cortex, V2. So it's in V1 that you get these cells that respond to a particular angle. Now, in V2, you may have things that respond to movement. So a cell may respond only if you have a line at a particular angle moving in a particular direction. And then as you move on to higher levels of visual processing, you get more sophisticated features. Sorry, I just mentioned further about these experiments with the cats. The other thing they did is they did experiments where they had they raised cats from birth. So when a cat is born, for the first several days, its eyes actually stay shut, and then at some point they open their eyes. And again, it's a bit cruel what these people did, but they would put these cats in an environment where they never saw any vertical lines. They only saw horizontal lines. And what would happen is that this system wouldn't develop properly, and then they actually weren't able to see vertical lines. So these cats, if you then put them in an environment where there's vertical lines, they would sort of tilt their heads sideways so that they could see. Now, I should say there was a bit of controversy about this because at the time, Hubel and Wiesel originally claimed that there's some critical period, and that if these cats were not exposed to the vertical lines within a certain period, then they'd sort of never be able to see them. But actually, we now know that that's not really true. So if after performing this experiment, you then put the cats into a normal environment, after some period of time, they will be able to see the vertical lines, right? So the brain does remain plastic later in life to more than what was thought at one stage.
Maybe this is a bit off topic.
Yep.
What do you mean they can't see horizontal lines? What do you mean? Like they can go into their head, right? In their eyes. Or what do you mean they can't see?
In the well, there is a period of time where they can't see them because they don't have the neurons that will respond. Yeah, it gets into their eyes, it gets to the retina, it goes back to the visual cortex, but then there aren't yet neurons in the visual cortex that respond to lines at that angle.
Like recognize the pattern. Like,
That's right. So they have to turn their head to sort of make sense of it. Yeah, I know what you're saying. If you wanted to ask them what they perceive, you would have. Well, we're not allowed to perform those experiments on people, so we wouldn't be able. If we could perform the experiments on people, then we could ask them, well, what are you actually seeing? But we're not allowed to do that. Yeah. So whether they actually see them, it's very hard to say whether it's just invisible to them or whether they see it in some sense but can't really make sense of what it is. Yeah, I don't know. Yeah, very good question. Okay, so the main reason I'm talking about this is that this really forms the background for a particular section of the course, which is to do with image processing and convolutional networks. So we'll get to this probably in weeks 3 and 4. So these modern image classification networks are, to a large extent, are based on this work of Hubel and Wiesel. So we build artificial neural networks. They're called convolutional networks. So we have neurons in here which play the same role as those neurons in the primary visual cortex. And then at the next layer, we have neurons that we think perform a sort of similar role to in the secondary visual cortex. And then we have some fully connected layers, and then the network tries to say what the animal is. So I'm just presenting this as one particular good example of where neuroanatomy studies of the brain have actually given big clues as to where these neural networks really are based to a large extent on the study of brain structures. And this is a picture. This is if we try to visualize what feature. So each of these artificial neurons responds to a particular pattern. So once we've trained such a network, we can ask ourselves, well, what is the input pattern to which a particular neuron would most strongly respond? And interestingly, they do correspond in some sense to the kind of patterns that Hubel and Wiesel found with their experiments. So these are not, this is sort of, this neuron would respond to a pattern where there's a line here that's brighter than, let's say there's a line in this particular direction that's brighter than what's on the left, on either side of it. Excuse me. So, yeah, there are some features that respond to lines in particular directions. Maybe there are other features that respond to other things. So this would respond to an image which is particularly pink. or particularly blue or whatever. So these are networks in the first layer. And then when we go to higher layers, we see neurons that respond to more sophisticated kinds of patterns. I think this network was trained on images of motor cars. So it's a bit hard to tell at this resolution, but it's actually, this neuron might be particularly good at detecting a wheel or something like that. So we'll talk in a lot more detail about this when we get to that part of the course, but I just wanted to mention this. Now, and then I slipped in a couple of slides here just to show the other kind of tasks that we're going to be looking at. So we'll spend a couple of weeks on this, on that image processing. And then we'll spend a couple of weeks on language processing or sequence processing. Now, this, I mean, crudely speaking, with language processing, you have a sequence of words coming in one after the other, or whether it's words, whether it's letters, whether it's phonemes or morphemes or whatever. Let's say it's words. So you get one word and then the next and then the next, and the meaning of the sentence may depend on the whole sequence of words. So what you have is a bunch of neurons in here. You feed in one word, and then you do one step of computation, and then you feed in another word. And what happens in here is dependent on the previous state of this system as well as the new word. So this is called a recurrent network, and we can kind of think of it as unrolling. So you've got, this is a bunch of neurons at the beginning or after you've heard the first word. And then what happens after you've heard the second word is dependent on the second word and as well as this previous state. So each state is always dependent on the previous state and the new word. And sometimes sometimes you process a whole sentence before you produce any output if you're doing, sentiment analysis. Or if you're doing some other task like translation or segmentation, then you might be producing an output at each time step. So we'll spend a couple of weeks on this kind of stuff. So recurrent neural networks and language processing. And then we'll look at deep Q learning. Now again, these are things that we don't really know very well how the brain actually does these things. But this is where we're just looking at learning of Atari games, let's say. So the input, you have a system that's just being presented, these old Atari games from the 1980s with a fairly low resolution input. And so you're just given a sequence of screenshots, and you have 18 possible actions. So this joystick can be in 9 different positions, and you can press the button or not press the button. So there's 18 possible outputs, and we'll be looking at deep reinforcement learning, are methods where just from observing the sequence of inputs and monitoring the score that you're getting, you can learn to choose actions in a way that'll maximize your score. And so in a way, this is meant to mimic, I guess, in humans, learning from experience or learning to perform tasks and so on. But again, this is sort of we don't understand well how this happens in the brain. So we'll do the image processing, the language processing. We'll spend a couple of weeks on this reinforcement learning stuff. And then at the end of the course, we'll talk about autoencoders and generative models. So just briefly, what these autoencoder networks are is that you're not, so let me see here. If we go back to, so if you think about the task of image classification, this is sometimes called a supervised learning task. You're given an image and you're told this image is a dog, and this image is a bird. So you're kind of told, you're given the image and you're told what class it is, and you're given like 1 million images, and for each one you're told what class it is. So the image, this famous ImageNet database, there's 1,000 categories and there's 1,000 images in each category. So there's 1,000 images of a bird, 1,000 images of a dog. So the system is trained on those million images, and then afterwards you give it new images and ask it to guess what kind of object it is. That's called supervised learning. With these Atari games, this is called reinforcement learning because you're not actually told. If it was supervised learning, you would be given the screenshot or a few consecutive screenshots and then told, well, the correct action for this is action number 5. But usually we're not told that. You know, the system just has to try out different actions and it's told how much reward it's getting. So that's called reinforcement learning. And then what we'll look at the end of the course is sometimes called unsupervised learning. In this case, you're not actually told inputs and outputs. You're just given images and you have to kind of you have to try to extract some information from those images. So this is sometimes done with an autoencoder, or another task might be you're given a set of images. Let's say you're given a set of images, in this case of bedrooms, and then you want your system to generate new images, you're given a set of real images of bedrooms, and then you're asked to generate synthetic images of bedrooms. You know, so this becomes a generative model. So it's saying, I want you to generate images which are kind of like the images that I've given you, but not exactly the same. And it turns out there are methods that can do this fairly well. So all of these images here are actually synthetically generated images of bedrooms, but they look fairly realistic. These are a couple of years old. Some of these methods have been refined since. If you look closely at these images, you can often see funny little anomalies. You know, you might see the wrong number of taps in a sink, or you might see like windows that kind of, I'm not sure what a good example is, but you know, beds that are kind of Siamese beds that are slightly split in half or something like this. You see things that we recognize as being not quite correct, but in general these images do look pretty convincing. And then this last slide is just mentioning something that may be interesting in the future. So real neurons have this sort of pattern of spiky. So the voltage builds up and a signal goes along the axon. And if you actually monitor these things, you may see a regular pattern. So you might see, depending on the stimulus, you might see a neuron firing like this. It might fire and then fire again, or it might fire quicker in this very regular pattern, or you might see a few spikes and then a delay, a bit of irregular pattern, or you might see like a lot of spikes and then a quiet period and then a lot of spikes. So normally with neural networks we kind of abstract away this kind of complexity. instead of seeing the spike pattern, we just have a number which represents the spiking rate. And we have simplified models. But there are some people who say that actually important information is carried in this pattern of these spikes. So there's some work these days where people try to make more realistic models of neurons that actually retain this kind of spiking pattern. But so far, people aren't quite clear how to train these models. But this is something that might be important in the future. Okay, any questions about this? All right. I just got back yesterday from a conference in Brazil, so I think I'm doing okay with the jet lag so far, but if I fall asleep, please come down and wake me up. Okay, so I think where are we? 8 o'clock. Yeah, I realize there's a lot for one day, so let's just do. This will be the final topic for today. We'll talk about the perceptrons, and then next week we'll talk about the backpropagation. Okay, so this is the picture I showed you of the neurons. Now, as I mentioned, real neurons have a lot of this complexity about the chemicals and the neurotransmitters and so on. But what we want is just a simplified mathematical model of a neuron which captures the essential features but isn't too complicated. So what are the essential features that we really have to have in a neuron? Well, it's got a cell body. It's got dendrites. So the dendrites are, as I said, are inputs from other neurons. The axon is the output. And then there are connections, and they can be excitatory or inhibitory. So if we want to build a mathematical model of this, we can say, all right, well, each neuron is connected to other neurons. So there's each neuron is receiving inputs from other neurons. And so we can draw a graph of neurons. We can draw a graph where each node in the graph is a neuron, and then each connection shows that one neuron is connected to the next neuron as a directed graph. And then we can have a weight on each edge which says how strong the connection is between one neuron and the next, and whether it's excitatory or inhibitory. So if it's a positive weight, that means that if this neuron fires, it's more likely for the next one to fire. If it's a negative weight, it's less likely for the next one to fire. And then each neuron has an activation level, which is like the voltage inside the neuron. So then what happens is if the inputs of a particular neuron are well, let's say we have a neuron which is taking two inputs. So we start with just so for today we just talk about one neuron. Later on we'll talk about connecting neurons together. So you have this neuron is just taking two. We just think of this as taking two inputs. All right. Let me just. I know some of you, those of you who took some of you from a previous course may know about this already. But just to make it concrete, maybe I talk a little bit about Rosenblatt and what he was doing. So. This is a picture of Frank Rosenblatt, a very serious man, obviously. And he had this idea, okay, I don't want to model the whole brain, I just want to model one neuron. And maybe that one neuron is enough to do some kind of computation. And the task that he was interested in was letter recognition. So he would draw a really big letter on a wall, and he'd have a camera that would take a picture of that letter, and then it would get translated into a sort of image that was maybe 20 by 20, let's say. So that's 400 inputs. So you have an image which is 20 rows and 20 columns, and so there's 400 inputs, and the input at each point is the intensity of light at that point. Right? So that's his inputs, and then his outputs would be what letter that is. So he would train, if there's 26 letters, he would train one network just to recognize the letter A. Is this letter an A or is it not an A? And then he'd train another network to recognize a B and a C and so on. And so if he's given a letter and he wants to know what one it is, he feeds it into each one of these 26 networks, and whichever one is most confident that it's that letter, that's the one he chooses. Right? So this kind of makes the thing a bit more concrete. So he got 400 inputs, and for each, there's 26 outputs, but we can think of it as 26 different networks, each with only one output. Right? So it's trying to say whether it's that particular letter. And he was doing this in the 1950s before the invention of the transistor. So it actually, his hardware consisted of vacuum tubes. So you see there's a bank of vacuum tubes. And I had another picture which shows all the wiring. It looks like just this mass of spaghetti. So it shows you the primitive conditions that he was working under. Okay. So he had 400 inputs, so x1 up to x400, but I've just drawn two inputs here, x1 and x2. And the idea is he's only modeling one neuron, so there's a weight from each input, and it really just shows you how likely it is that a particular pixel in the image would be lit up for a particular letter. Sorry, let me just... I know I'm laboring this a bit, but I think it's important to make this, make this tangible. Let me see if I can... get an image here. Okay. So you think about this, let's say you're trying to recognize the letter C. Well, you can kind of... Why is that funny? Now, again, he had a very simplified situation where he sort of tried to center the letters and make them a regular size and so on. So if, let's say that let's say the C is a white letter on a black background, or let's say it's a black letter on a white, let's say it's a white letter on a black background, then it would be reasonable to say if this particular pixel is white, then that's makes it more likely that the thing is a C, right? But if this pixel is white, that makes it less likely that it's a C. It's more likely to be an I or something, a letter that covers the middle. And then pixels here would distinguish between a C and an O. So a C and an O are pretty similar. But if you wanted to tell the difference between a C and an O, you would want to look at pixels like this. If this pixel is white, then it's more likely to be an O, right, and less likely to be a C. So you can kind of imagine for any one of these pixels in the image, you could get an idea whether, that pixel being white or black, whether that makes it more or less likely for the thing to be a C. So this is what he's trying to learn. Okay. All right, so we have x1 up to x400, and for each input we have a weight, and the weight serves the purpose that I described. So if we want to eventually get a number that says whether the thing is a C or not, so we add up each input multiplied by the weight, right? So the input maybe is some number between 0 and 1. 1 means it's completely white. 0 means it's completely black. And then the weights can be positive or negative. So you multiply each pixel by the corresponding weight, and you add that all up, and you get a linear combination. And then you have a certain threshold. So if that linear sum is above a certain amount, then you say, yes, I think this is a C. If it's below that amount, you say, no, I don't think it's a C. Right? Now, if the it's a bit of a mathematical convenience. Instead of adding up everything else and then checking whether it's bigger than the threshold, we could add everything else. We could add everything up and then subtract the threshold and see whether the answer is bigger than 0. And instead of subtracting the threshold, we could add the negative of the threshold and then see whether the whole thing is bigger than 0. So often, instead of subtracting theta, we add this number called W0, which is the negative of the threshold. So this is just a mathematical convenience because it turns this into a linear sum. Okay? And the W0 is sometimes called the bias. The reason it's called the bias is the bigger the W0, the more likely it is that the neuron is going to say, yes, this is a C. The lower the W0, the less likely it is to do that. Okay? So we get this picture where we add every input multiplied by the corresponding weight, and then we add the bias, and we check whether that result is bigger than 0. And then another way to think about this W0, we could imagine that there's a special input whose value is always equal to 1, and then W0 is the weight associated with that input. So again, these things it's all just like different ways of seeing things that are mathematically equivalent. Okay, are there any questions about this? Yeah. So this is called a Rosenblatt perceptron. And so originally, so you see what's happening here. There's a linear part and then a nonlinear part. Now the nonlinear part here is just testing whether the thing's bigger than 0 or not. So if this sum is smaller than 0, then the output will be 0. If this sum is bigger than 0, then the output will be 1. So we can draw this nonlinear component as we call it a transfer function or an activation function, and it simply produces 0 for numbers less than 0 and 1 for numbers bigger than 0. This is sometimes called the Heaviside function. And this is what the perceptron is based on. Now later on, and we'll get to this next week, later on this was replaced with a sort of smoother function and so on. But for the moment we just think about this as a threshold function. Okay, so I think it's again, like I know some of you have seen this before, but I think it's useful to go through one of these examples by hand. So let's suppose we want to compute. So one example is if we think about logical functions. Let's say we want to compute the AND function. So I think, let's say we treat 0 as false and 1 as true, and we have two inputs, x1 and x2, and what we want to compute is the logical function x1 and x2. So the way we would draw this is we say that this is 0 and this is 1. So if in order for the output to be 1, both inputs have to be 1, right? So if these are both equal to 1, then the output should be 1, and if it's both 0 or one of them 1 and 1 0, the output should be 0. So we get this kind of picture in 2 dimensions, and we draw each data point as a circle, and if it's a filled-in circle, it's a positive example, and if it's not filled in, it's a negative example. Okay, so if I draw some data like this, then you can draw a line which separates the positive data from the negative data, right? So things on this side of the line are positive and things on this side of the line are negative. And you can draw any line. You have multiple choices of lines you can draw, but this line here is the best in some sense because it gives the maximum separation between the points. And so if we want to compute the equation of that line, we can go back to what we remember from high school and use the slope and the y-intercept. So the slope is equal to -1, because if we go 1 unit here, we go 1 unit down, and then the intercept, the best possible intercept is 1.5. So the equation of this line is x2 is equal to 1.5 minus x1, or x1 plus x2 minus 1.5 equals 0. Now that's the equation of the actual line, but what we want is actually an inequality that tells us where the positive examples are. So if you think about this positive example is 1 and 1, in that case this plus this minus this is bigger than 0. So the positive examples are where this is bigger than 0, and the negative examples are where it's less than 0. So this gives us an inequality, and from this inequality we can build a perceptron, a little neural network with one neuron. So we say, okay, our perceptron looks like this. We have the input x1 and the input x2. This weight here is +1. This weight here is +1. And then we have this bias, which is minus 1.5. And that gives us a little perceptron. So this is saying that we take x1 plus x2 minus 1.5 and check whether that's bigger than or less than 0. And that tells us whether the thing is positive or negative. Okay. Is any questions about this? Yeah. Okay. So if I give you any data, if I take out a piece of paper and I draw a bunch of positive and negative examples, you can, by hand, you can design a perceptron that will classify these examples. You just take out a ruler, you draw a line with the positive examples on one side and the negatives on the other, and then you calculate the slope and the intercept of that line and figure out which side the positive examples are on, and then that gives you your perceptron. Okay, so now in order to do this, the examples have to be linearly separable, right? If I had a positive example, let's say I had these data, but then I also had a positive example over here, well then you wouldn't be able to have a perceptron to do this task because you wouldn't be able to draw any line that separates them. Okay, but as long as that line exists, then we can calculate the weights for the perceptron. Now, okay, but let's think back to Rosenblatt's problem. He had 400 inputs, not 2, right? So you can't take out a 400-dimensional piece of paper and draw a 399-dimensional line, right? So then he said, well, I need to figure out a way of learning these weights. I want a system where I give it some C's and I give it some letters that are not C, and I want it to learn for itself the 400 weights for this perceptron. Okay. And this is his perceptron learning rule. Okay, so this will be the last thing for today. We'll look at this algorithm and some examples, and then that'll be it. Okay, so this is his algorithm, yeah, and I apologize, I know some of you are familiar with this before, but some of you aren't. So you present the examples one at a time. So, you know, you have, let's say you have 1,000 letters, of which some of them are C and some of them are not C, and you look at the images one at a time. So you start with just some random weights. And then you have this variable eta that's called the learning rate. So I present the first image and I calculate the output based on the current weights of my network. And the output is either 0 or 1. Now, if the network classifies that image correctly, we don't do anything. So let's say you give it an image that is a C and it outputs 1. Well, it got the correct answer, so I don't change anything. Or you give it an image that's not a C and it outputs 0. Well, again, it got the correct answer. So the only time we change the weights is if we present an image that is a C, but it outputs 0, or we present an image that's not a C, but it outputs 1. So we only change the weights if it gets the answer wrong, right? Now, okay, so let's suppose that we have an image that is a C, so the network was supposed to output 1, but actually it outputs 0. So then Rosenblatt's thinking to himself, well, okay, I need to change the weights in such a way that when I present that particular image, the linear sum will be a bigger, right? Now remember, this sum is of that form, so W0, if I increase W0, then that'll increase S, right? So I'm going to add a little positive number to W0, right? So you have to have this number eta. We could assume that eta is 1 for the sake of this. It doesn't really matter what eta is, but it's some fixed number. Okay, so let's say I add 1 to W0. So that definitely will increase S. Now, and then x1, and then I add eta times x1 to W1, right? So the problem is I can't just add 1 to all of these weights because some of these inputs might be negative, or some of them might be smaller than others. That pixel might be black anyway. So the trick is, instead of just adding a constant to each weight, I add a constant multiplied by that input. And so if I add eta times xk to wk, that means I'm adding eta times xk squared to s. So xk squared is always a positive number, right, or a non-negative number. So if x is negative, if xk is 0, then if x1 is 0, I don't bother changing w1 because it's not going to make any difference to s. If x1 is positive, I add a positive number to w1 so that s will increase. And if x1 is negative, I add a negative number to w1 because that will make s increase. Okay, so the sign of w1 has to, I have to change w1 in a direction which matches the sign of x1 for that particular image. Yeah. So this guarantees that the next time I present that image, s will be bigger by this positive amount. Okay. And notice also I change the weights whose inputs are biggest get changed the most because they're the ones that are going to make the most difference. Now, conversely, let's suppose I give an image that is not a C, but the network thought that it is a C. Then I have to decrease S, so I just do the reverse. I subtract a positive number from W0, and I subtract a multiple of xk from wk, and that will decrease s by this positive number. Okay, so I do this for the first image, and then I present the next image and go through the same process. And if there's 1,000 images, I go through all of them one by one. And when I get to the end, I start again from the beginning. I go back to the first image, and I keep looping through. And Rosenblatt proved that as long as the data are linearly separable, eventually this process will stop. Eventually you will reach a point where it correctly classifies all of the images. Okay, so this is just an I'll just quickly go through the example. You can look at the details of this in your own time, but let's say we have a learning rate of 0.1, and let's say that these are the random initial values for W1, W2, and W0. So this is this is the inequality that the weights are currently computing, and I can draw that like this. And then I'm given this item, and I'm told that this is a negative example. So this is a negative example, but the current weight's classified as positive. So I subtract eta from W0, I subtract eta times x1 from W1, and then I get a new set of weights. And the new set of weights define this line here. And so then I'm given a new training example. And this training example is meant to be positive, but it turns out that it's classified as negative. So I add eta and eta x1 and eta x2, and then I get this new set of weights. Now, maybe the next set of weight, so this example maybe is correctly classified. This point here is positive. If you plug these numbers into here, it turns out it's classified as positive. So for that data point, we don't change the weights. And then the fourth data point is here, and it's negative, but it's classified as positive. So then we decrease the weights. So this just shows you the first few steps of the process. And if you keep going through, as I said, you go through all the data once, and then you go through it again, and you keep going until at some point eventually it classifies all of the data correctly. Okay, any questions about this? Okay, just a few slides left here. Okay, so these are some examples. So this example we worked through by hand, the one on the left, that's the AND function. I mean, these are some other examples, the OR function. Now, but a lot of examples are not linearly separable. So it's interesting, in machine learning, if you go out into industry and someone has a machine learning problem, in a lot of cases it is actually linearly separable, or a linear function will do a reasonable job, but there are a lot of other examples that are not linearly separable. So the simplest example of a function that's not linearly separable is this function here called the XOR function. So I've got two positive examples here and two negative examples here, and it's easy to see that there's no way to draw a line that puts the black dots on one side and the white dots on the other. Okay. And this was essentially so this is the limitation of perception. This was the essence of Minsky and Pappert's book in 1969. They said, well, perceptrons are really dumb. They can't even learn something as simple as XOR, right? Now, how could we actually learn a function like this? Well, one way is to break this down into simpler functions. So I don't know how much logic you know, but this is this dot here is where this dot here is x1 and x2, and this dot here is x1 is not x1 or x2. So we sometimes call that the NOR function. And so you can logically say, one way, there's several ways to logically break this down, but one way is to say, well, I don't want this and I don't want this. You know, so I can compute x1 and x2, and I can compute x1 nor x2, and then I say I want neither this nor this. So I can put together a little network. I can't compute this with one neuron, but I can put together a little network of 3 neurons, and between them they all compute XOR. Okay, so this is x1 and this is x2, so this computes x1 and x2, this computes x1 nor x2, and this computes this nor this, and logically when you combine all this it actually computes XOR, which is what we want. Okay, and if we know we can, each of these component functions is linearly separable, so we can draw a line and do the calculation and come up with these weights. Okay. So this was known in the 1960s, and in fact, if I write down any logical expression at all, if I have 20 variables and I write down some logical expression in those 20 variables, it's actually possible to construct a 2-layer neural network that computes that function, because you can convert the logical function into what's called conjunctive normal form, and once it's in conjunctive normal form, that tells you, it breaks it down into little components, and you can make one neuron for each of those components, and then you can combine them all together. Okay, so that was known in the 60s, but what was not known in the 60s was how to train a net. So normally you're just given a bunch of data, you're not given a logical expression, you're just given data. So what was not known is how you could train the weights of a neural network to learn those data. So what we want is an equivalent of this perceptron learning rule for multi-layer networks. Okay, and let me just, I know we're nearly out of time, but I just want to make one more point and then we can go. So the main reason that if you think about this, well, why can't I just use the perceptron rule? When we only had one, because we only had one neuron, by checking whether this was positive or negative, we could immediately tell the right way to change those weights. But because we've got this network of neurons now, we kind of have what's called the credit assignment problem. So if I have a network with certain weights, and then the whole network, I put an input and the whole network produces the wrong answer, there comes this question, well, which part of the network is wrong? You know, so you can think of this as like a company, you know, this is the head office and these are the two branch offices, you know, like, and then if the output here is wrong, you know, this guy can say, well, I'm pretty sure I output the right thing, but it must be that other guy over there output the wrong thing, and that's why the answer was wrong. And this guy can blame that guy. Well, his answer must have been wrong. And the top guy can blame both of these guys. You know, I'm sure I'm putting this together correctly. These guys must be giving me bad information. And they can all blame each other, right? So this was like the stumbling block that kind of held up this research between 1969 and 1985. Okay, so next week we'll talk about how this was solved by using backpropagation.
I assume for this XO from 2D.
Yeah. Oh, yes. That's right. Yeah, exactly.
Yeah, so that's why this is the one.
Yeah. That's right. And then they do become linearly separable in the third dimension. Yeah. Yeah.
What about the handwriting? Like it's a little bit weird, like not standard. So like how do you recognize it? Like,
Yeah, exactly. That's a good question. So this early work was only able to do it if the letter was written in a very standard way and was centered and so on. Now there's this famous database called the MNIST database. It's not letters, it's digits. And it's from the Canadian Postal Service. They have 50,000, they have 5,000 examples of each digit and they're handwritten. And so, yeah, perceptron can't really learn the job well, but that's why we need multi-layer neural networks in order to handle different styles and different kinds of handwriting and so on.
you just talked about like there's like 50,000
Yeah.
database, right? So what's the difference between a knowledge base that you talked about early in the lecture about like a doctor try to different patients, different doctors they give
Yeah, these are good questions. So if you go back, let's say to the 1990s, people tried to do letter recognition by these hand-coded features. Like they'd take the image and they'd try to calculate certain features like the entropy or the density, or they'd look for, if they're looking for a T, they'd look for a particular kind of pattern. So it was based on expert knowledge, and then they would like linearly combine those handcrafted features. But the modern approach, the features are not handcrafted, they're just automatically learned.
But we still need to provide like a database.
That's right. Yeah, we need a database, but we don't need to provide sort of handcrafted features.
Yeah, we don't need the rules for that. Like,
That's right.
Like crawlout, we don't need to provide those rules.
Exactly.
Thank you very much.
Yep. So for the neural network there, do you need to, like, for example, the AND gate and the NOR gates, do we always get 0 and 1 output for each single perceptron? So we apply transfer function to each single perceptron.
That's right.
Okay. So, yeah, okay. Because I'm thinking that if we get different things like 0.5 or negative 0.5, that will do a lot of work for.
Yeah, you're thinking ahead. That's right. So this is partly, this is actually kind of partly the solution to this problem. Is instead of just having 0 or 1, you need to have like a smoother. You need to have a continuous output. That kind of smoothly varies between 0 and 1.
Yeah.
Then you have a better chance of adjusting the weights.
Okay.
Assignments, how many are they can be done as group assignments?
We think that the second we think what will happen is the first assignment you have to do yourself, but probably the second or third assignment you at least.
I was wondering about the lecture recordings.
Yeah.
Where can we actually access them?
Good
Because
question.
there isn't actually any Moodle page for the subject.
Yeah, I think I'll look on. Sometimes it takes a few hours for it to get processed, but I'll try to put a link on the course webpage.
Okay, cool. And you said there were like activities that we had to do for things like TensorFlow and stuff.
Yeah, I haven't. In the next few days, we'll put that up. Yeah.
Cool, thanks.
Basically, the same question as them. So,
Ah, yes. Ah, yes.
So when in the transcript would it be managed for assignments because that might be an issue with the
Probably be 9.444. Oh, you think just because it's different from what you said?
yeah, so that it's 9.444. I will just email them that I'm doing the same course, but I can just explain.
Yeah, I
it.
think just explain the course code will change.
Yeah, okay, yeah.
I'm sure it'll be fine.
Yeah, they should do. Thank you.
oh yeah,
Ah, yes. Ah, yes. Yeah, that's fine. We'll try to open up more space as well.
Yeah, 590. That's
I know. Oh, so you're you're a PhD student, yeah.
Not at all, no, masters.
Oh, masters, okay. Yeah, that's fine. Oh, yeah. Did you ever take any data structures course or anything?
Not at all. Though during my undergrad, which is computational design, we had a final semester which was a research semester.
Yeah.
And I learned
Right. Oh, it's mastered by research, is it?
It is, yeah.
Okay,
It's called a Masters of Philosophy.
Yeah.
But it is still research.
Okay. But yeah, we'll try to open up some It's full at the moment, but we'll try to open up some more places.
I'll be going through the JRS, like the research school, and they'll be able to add me even though it's full. So that's fine.
Okay, that's good.
I mean, that's what I am.
Yeah.
Thank you very much.
I think I found the phone on the ground. Like,
Oh my god, okay.
and it's locked, so I don't know what to do with that.
Okay, yeah. Hold on. Yeah, I'll take it up to use that queue in the morning. Yeah.
Okay, yeah, that would be wonderful.
Great, thank you.
Yeah, see you.
That's the text. Well, it could represent
Yeah, I mean, this is the neuroanatomy is not really examinable.
Alan, sorry, can I steal this piece of paper momentarily? Just to
yeah,
show
yeah,
them
yeah,
something.
Okay, sure.
That's the only part of the textbook.
Yeah, it's only returns one when.
Okay, sure. I'm just scrolling through this website.
Yeah, you can try and find
So
X1
that's
and X2.
chapter 9.
It only
Right.
section X1 and X2.
Yes.
And the representative.
Sure, I think that makes sense.
One
But for
and one. Yeah,
the second one,
these are all zero. But
so
in terms of
I
perception,
presume that
like this is what
5.4,
perception
5.5 is for perception.
This X1 and X2 are like the two.
Yes.
Right.
But I went to
Say,
chapter 5,
like
section
you put in
4 and 5.
one and one. You get one times one.
Maybe
Plus
just
one times one is two.
Yeah,
Two
it looks a bit
minus
different.
1.5 is 0.5. Because 0.5 is greater than 0, then it returns 1. But if you put in 1, actually, so say x1 was 1 and x2 is 0. Then 1 times 1 is 1, 0 times 1 is 0. 1 minus 1.5 is negative 1, negative 0.5, which is less than 0. So then it doesn't reach that threshold